Hello friends, welcome to the lecture on the review of probability and statistics as a part of the course on introduction to statistical hypothesis testing. This is part 2 of the review. In the previous lecture, we learnt the concepts of probability, the basics of probability axioms, and we also studied the notion of a random variable, probability distribution functions, and in particular probability density functions for continuous valued random variables. Now, if I may connect with the overall purpose of this lecture and the previous lecture, what we are trying to do is we are trying to describe the truth or the population characteristics. Ultimately, we will not be working with the population, because what we mean by population is the large sample space that or the sample space that we have. We will not be able to work with that. In practice, we collect subsets or what we call as a sample, and then we work with the data resulting from that sampling, and then draw inferences about the population. So, what we are trying to do is we are trying to understand how truth is being described and what are the parameters of interest to us, and then gradually we will move on to the practical or the practicing aspects of hypothesis testing. So, in this review, what we are going to do is learn what are known as moments of a PDF, in particular the mean and variance, and we will also study the bivariate case. That is, until now, until the previous lecture, we have learned how to describe a single random variable, but very often we will deal with more than one random variable, for example, in regression and so on. We will not study the multivariable case, but we will study what is known as a bivariate case, that is the case of two random variables, in which situations we come across the notion of a joint probability density function or joint probability mass functions, depending on whether you are looking at continuous or discrete valued random variables respectively. In that context, we will study the ubiquitous, the most frequently encountered measure of relationship or dependence between two random variables, known as the correlation. So, let us begin our journey or continue our journey with the univariate case. As I said in the previous lecture, we came across the notion of probability density function, again to study a single random variable associated with a random phenomenon. Now, as far as theory goes, the probability density functions or the distribution functions are very nice to work with, but the question is, how do you obtain these probability density functions or even distributions? It is going to be quite a tough task. There are a few processes for which perhaps you can derive the PDFs or the cumulative distribution functions from the physics of the process. As I had mentioned, the book by Oganaike shows you how to derive the distribution functions when you know something about the physics of the process, but there are a large class of processes for which we will not be able to do that. We may not have the luxury to do that. So, how do you now deal with that? The natural recourse is to estimate or reconstruct those PDFs from data that we collect, and we know that it is impossible in general for a large class of processes to be able to obtain all possible outcomes. So, we end up with working with subsets of data, which we call as samples. Now, from this sample we are supposed to estimate the PDF. Now, if you turn to the literature on the estimation of PDFs or the probability density or distribution functions, there exists no highly reliable methods for estimating these PDFs. There are, it does not mean that there are no methods, there are methods, but they are not as reliable as those methods that exist for example, estimating averages, variances and so on. So, can we work with those methods that estimate averages or estimate variability and so on, and that is what we are going to talk about briefly now. So, if you look at it practically, knowing the PDF of a random variable is not going to be possible theoretically. if at all it is possible in a few cases it should be the case. Then as I said just now, you will have to conduct experiments. Now, the good news is in many situations you may not have to reconstruct the PDF. It may not be necessary to know the full PDF. As a simple example, suppose I am visiting a new city which I have never visited, and I need to make a decision on what clothes to pack in my bag. What type of clothes, should it be woolen clothes or cotton clothes and so on. So, that depends of course on the temperatures that prevail in the city. So, what would I do as a layman or even as a general user, traveler? I would actually go to the website or consult some book or someone and seek information about this temperature. And obviously, the temperature in a city can be thought of as a random variable because it is not predictable accurately on any day. So, it is meaningful to treat it as a random variable. However, if you think of it, very rarely do we ask for the PDF of that random variable. It may sound a bit silly to think of the PDF of the temperature in a particular city. Practically what we would be interested in is some basic so called statistics, the minimum, maximum, average and so on. And with these pieces of information we are able to make a decision, at least to begin with, some decent good decision that we can actually make on what kind of clothes to pack. The question is how many pieces of information, such information are sufficient to begin with. So, again going back to the same example, I would like to know, I need to know for example, what is the average temperature. That is the first piece of information that I would like to know. If the average temperature, let us say, turns out to be 10 degrees Celsius, then going from a tropical country to such a city would mean that I may have to pack clothes for or pack winter clothing. In addition, I would also need one information, which is the range of temperatures that one gets to see in that season during which I am visiting, which we call which we may either measure by minimum and maximum, which it will give us an estimate, or we look at the variability or what we call as a standard deviation. Once I know that, so let us say that this particular website tells me that the standard deviation is about 10 degrees Celsius. So, that means I can expect temperatures anywhere between 10 plus or minus maybe 2 standard deviations, 20 and so on. So, that is quite a lot of variation nevertheless. Nevertheless, it is just an example, so not to worry about it. And this 2 sigma interval that we look at is ideal if you think of this random variable following a Gaussian distribution and so on. But those are more detailed aspects of it. The bottom line is I am glad I am fine with knowing these 2 pieces of information as far as my decision making is concerned, and that is the case usually in practice. We are mostly interested in mean and variance and perhaps of course, if not mean, median and so on, which are representatives of the most likely value or the expected outcome and how far the outcomes are spread respectively. So, the mean tells me what I can expect when I visit the city, and the variance gives me an idea of what is the spread of the outcomes, what are the extremes that I get to see. So, to summarize, instead of working with PDFs, it is convenient to work with these 2 kind of statistics, you can say population statistics or 2 parameters of the PDF and so on. Now, it turns out that the mean that we are talking of is nothing but the first moment of a PDF. Now, many a times people have difficulties understanding or interpreting this probability density functions, but it is convenient if you take an analogy in mechanics of the mass distribution or the mass density functions. Typically, we talk of densities, which is mass per unit volume, but we can also talk of mass per unit length, right. We call this as specific mass. So, this density function that we are looking at is pretty much analogous to the density functions that we see in mechanics, and we know from mechanics we also have moments and so on, which tell us give us an idea of where the center of mass is, for example. We have learned center of mass, center of gravity and so on. Likewise, here we have a set of outcomes spread over a range, and we would like to know where the statistical center is. That is, what is the most likely outcome, or what is the expected outcome as we call. And for this purpose, we introduce this term called expectation. It is strictly an operator and typically denoted with the symbol E. So we write expectation of x as you see in equation 1 here, which is also conventionally denoted by the Greek symbol mu, and it is defined as minus this integral here running from minus infinity to infinity x times f of x dx. Now, this minus infinity to infinity should not be looked upon numerically, but more so symbolically. They represent the left and the right extreme values for the single random variable. And we know that this integral is the first moment of the PDF, again from mechanics. Now, strictly speaking, there should be a denominator in this, and that is often avoided for a reason, and let me tell you that. So, we have mu as integral x f of x dx in the expression. However, strictly speaking, you are supposed to have an integral f of x dx also. Now, probably you are in a much better position to relate to the expressions that you see that we get to see in mechanics. Of course, the limits are the same, integration limits are the same on both integrals, but we know by definition of the probability density function that the area under the density function is unity, and therefore, this is avoided. In fact, we talked about this, any function to be called as density function should satisfy this criterion. So, it is assumed that we have already done some kind of a normalization, so that this legitimate requirement is met, and therefore, we do not need to write this anymore. It is understood, it is an invisible denominator which is unity. All right. Now, of course, we are talking about continuous valued random variables here, and there is also another interpretation, a rough interpretation that you can take from this integral. Approximately, if you think as the integral as a summation, after all integral is a limiting case of the summation, then and if you divide the outcome space very finely, let us say it is a continuous valued outcome space or sample space, and you divide it very finely into a grid and call the ith point on the grid as xi, then you would say f of xi dxi here. So, you have the integral being replaced by a summation approximately. So, look at what this expression carefully now, you have xi times f of xi times dxi. This f of xi dxi is the probability of this random variable taking on values in this infinitesimal interval xi and xi plus dxi. So, this is it is a probability that the random variable will take on values in this small or infinitesimal interval. So, what you are saying is that the average value is the particular outcome weighted by this probability, and this is what one gets to see for discrete valued random variables. For discrete valued random variables, you will not see integrals, we will see summations. In that case, we replace f of xi dxi by the probability of x taking on that value itself, but this is continuous valued case, therefore, we tend to write this way. So, this kind of helps us remember or probably get a better interpretation of this integral. Now, this expectation operator is a fundamental operator in all in the entire theory of probability, and one needs to be quite comfortable with computing expectations. Of course, in hypothesis testing it may not be required, but what is required is interpreting this expectation in a correct manner. Whenever we compute expectation of a random variable x or expectation of any function of that random variable, what we are essentially doing is computing the statistical average, or you can say the ensemble average or the average across the population and so on. It is not the average in time at all. It is often misconstrued and misconceived as being average in time. There is no notion of time here. The expectation is an averaging operation that is being performed across the entire population space. In fact, the expectation of g of x is nothing but integral g of x times f of x dx. So, g any function of a random variable is also a random variable, that is the first point, and therefore, it would have a statistical average, and that is once again written this way, and you can give a similar interpretation as we have given here. Whenever x occurs, you can calculate g of x, and that is weighted by the probability. So, you are actually again doing the same thing. We use this expression to compute or to come up with the definition of variance, as we shall see shortly. So, let us go through a couple of examples on computing the theoretical or the population mean. Let us say I have a random variable that follows Gaussian distribution, and I want to determine the mean. Now, the first piece of information that we require to proceed is the density function, and we know that the Gaussian density function has this expression 1 over sigma root 2 pi exponential of minus half x minus mu by sigma to the whole square. Therefore, I plug in that expression for f of x in the definition of mean, and if you work out the integral, of course, you need a bit of math here, and I am skipping all of that. Eventually, the answer works out to be mu, and that is why we have been using the symbol mu in the first place itself, right. So, that tells us why we have used mu in the PDF. And going to the second example, suppose I have a random variable that follows a uniform distribution. Now, we know that the uniform distributed random variable has a PDF in the interval a comma b as a 1 over b minus a. Then the expectation is once again integral x times 1 over b minus a dx. Running from a to b, because those are the left and right extremes, and it is clearly b plus a by 2, that is intuitive. So, what is important here is that the mu that we are seeing is the statistical center, it is not necessarily the geometrical center of the outcomes, and I will talk about it briefly. But in these two distributions, both Gaussian and uniform distributions are symmetric about their means. Therefore, the statistical center and the geometrical center work out to be the same. Now, as I mentioned, so I just want to go through a few, make a few remarks on the mean itself, and then I will again come back to the statistical center and geometrical center part. So, the integral in equation 1 is across the outcome space, as I had mentioned earlier, and not across the time or any other spatial or frequency domain. And wherever you see expectation, henceforth you should think of it as an averaging operation. And of course, there is a reason why we have given that name expectation, we will talk about that. There are other measures for the center of outcomes. Mean is not the only measure of the center. Remember, the reason why we are working with mean is we want to know the point around which the outcomes are anchored, and that will first help me establish where in the space of real numbers the outcomes are anchored around. Like in the city visit example, what is the center around which central or the temperature around which the temperatures during the season that I visit are anchored. So, another alternative is median. Now, we know that the definition of median is that value which divides the probability distribution into two equal halves. So, let me explain that. So, the theoretical median, the definition of median is defined as the center, the point at which f of x hits the value of 0.5. which f here, this is a probability distribution, not the density. We know that by definition f of x is the probability that x takes on less than or x takes on values less than or equal to pre-specified values of x. So, here is the median, which need not be, it depends on the distribution whether this median is exactly, so suppose here I have the extreme value. Now, let us say 0 and let us say here this is x max. This median need not coincide with the geometrical center. So, now we are talking of statistical center and geometrical center. So, if you look at it exactly based on the schematic that I have drawn here, the geometrical center is here and let us assume that here is a distribution which coincides such that the median coincides with the geometrical center. Now, this occurs for symmetric distributions, for example, for Gaussian distribution and so on, but you can have another kind of a PDF which for example, here that goes this way and the 0.5 probability is achieved here. So, here is the median, right. This is also legitimate probability distribution function, but now the median is here. In this case, the median is not coinciding with the geometrical center, and same explanations can be given for mean as well. The mean is just a statistical center. Now, it is best understood from a prediction viewpoint. Suppose you are visiting, now going back to the city visit example, suppose you are predicting in your mind, essentially that is what we are trying to do. We are trying to predict what would be the temperature on the day I land, for example. What is that single number that I can use as a prediction for the temperature on the day I land, and that single number if you call as C, what kind of prediction do you want to make? You want to make a best prediction, but best in what sense? Well, we want to predict in such a way that we minimize the average error from all possible outcomes. So, for example, here this is the axis for x, and let us say the outcomes are spread anywhere between this x min and x max, and there are outcomes along this continuum, and I want to predict in such a way, that is, the C is that prediction. Let us say it is somewhere here, I do not know where it is, the C to be in such a way that it is at a minimum distance from all possible outcomes on an average, but which average? Statistical average. So, this we call as the minimum mean square error criterion. So, the mean has a very nice interpretation, because now the solution to this, you can actually solve this. If you say find C that minimizes this objective or cost function, you will find that C star is nothing but the expectation of x. Just using standard optimization techniques, you can arrive at this solution. So, what does this tell us? When I do not have any other information at all about the random variable, and I know, let us say, all the outcomes, or someone has let us say given me all the outcomes, then I simply take the average of all those outcomes, and that is the best prediction. It does not mean that that will be the value of the temperature on the day I land, it is not, but I am minimizing the risk, that is all. That actual realization that will occur will only occur when I land, and that typically will be different from C star. But if you were to look back on the day and ask, you know, if I wish I had made a better prediction, a very good prediction, in the minimum mean square error sense, this is the best prediction. And that is why intuitively perhaps we tend to work with averages, but having said that, it is best in some sense, that is, this mean is best prediction in some sense and not best in some other sense and so on, but we will not go into that. The purpose of this discussion is only to give you a better feel of the mean, right. As I said, you could also work with medians and so on, and there are distributions for which mean is much better suited than median and vice versa. Now, for symmetric, for Gaussian distribution, the mean and median coincide. That is something to keep in mind. Okay. Let us move on to the case of discrete valued random variables. As I said earlier, all that we do in the discrete case is that we replace the expectation with the integral in the expectation with a summation. Obviously, because now we are not dealing with continuous valued random variables, there is no notion of density, but rather we have a probability mass function f of x. So, this you should not get confused with the same notation that we are using. You have to interpret f of x in the context. If it is a discrete valued random variable, f of x is a probability mass function. If it is a continuous valued random variable, then it is a density function. As an example, suppose I am looking at a binomial random variable, that is a random variable which can only take which comes out of a trial, right. What is a binomially distributed random variable? Recall from the previous lecture, I conduct n Bernoulli trials, where I have n trials, and in each trial there are only 2 outcomes that are possible, with the probability of the success, as we call, as we label, being p, and then of course, other assumptions that this probability remains the same and each trial is independent of the other and so on. Then the number of successes, x successes in n trials with p being the probability of success, follows a binomial distribution. So, for such a random variable, the average is NP. It is fairly straightforward. All you do is you invoke the definition, that is expectation of x is simply sum of expectation of the individual trials, and that comes out to be n times p. You can work out the math. If you have difficulty, you can ask us. This is a standard example that you would come across. So, mean is the, as we say, you can say the first, not statistic, but per se you can say the first population statistic, you can say vital statistic of the PDF and so on, that we would be interested in, and that is easy to estimate. We have of course gone through only the theoretical definitions. The expressions for estimating mean will be given in the following lecture. The next quantity of interest to us, as we had discussed earlier, is a measure of the spread of outcomes. We have learned how to characterize the center of the outcomes. Now, we want to know the spread, how far the outcomes are spread around the center, and that quantity is variance, and this is a fundamental quantity in decision making. Now, at this point I also want to make another aspect of hypothesis testing or statistical inferencing clear, which is that until now we have been talking of random variables and we have been thinking of random variables being associated with a random phenomenon. However, random variables can arise in many other situations also. So, for example, let us say I want to estimate the mean. We have seen the theoretical definition of mean. How would I go about estimating the mean? I would collect some data. So, if it is average temperature that I want to estimate, then I would let us say in this room that I want to measure the average estimate the average temperature, I would come with a sensor and maybe install it at a suitable location, collect data maybe for about half an hour, and then let us say I have about 30 samples, or maybe I collect every half a minute. So, I have 60 samples, and then I am going to take the average of all of that, because intuitively we feel that that simple average will give me a good estimate of the true average, which I do not know, or the population average. Now, how did we construct this simple average? We have constructed this by simply averaging, adding up all the observations that I have. However, we should not forget that each observation is a random variable in itself. So, what I am doing is actually adding up all the random variables that I have, or all the 60 observations that I have, and coming up with a new random variable. So, the sample mean, as we call, is also a random variable. So, that will also have its own PDF, it will have its own mean, it will have its own variances and all the other moments that you can think of. So, now we should broaden our notion of a random variable from the simply as the outcomes of random phenomenon to operations on random variables, to include operations on random variables as well. When we do such operations, as we will learn in the next lecture, the sample mean that we are talking of x bar, let us say I have n observations, we just now said that this sample mean, as it is normally known sample average, is being constructed from n random variables. This also has the same DNA as this, that is what is the quality of that randomness. So, x bar inherits its randomness from the observations, therefore, this also is should be treated as a random variable and it has its own PDF f of x bar or mu x bar and so on, or maybe even variance as we shall define and so on. So, it is a random variable in its own right. Now, very often what we are interested in is this sigma square x bar, as will become very clear in the next lecture, because this is a measure of how much error we are incurring in x bar with respect to the truth. The truth is mu x, and the entire purpose of going through this is to get an estimate of mu, and sigma square x bar is a measure, in fact the square root of that is called the standard error, is a measure of how far x bar is away from its truth, and mu x bar is how accurate is an x bar as an estimate of mu. So, mu x bar is also important. In fact, if the mean of x bar, what is mean of x bar? Well, very simple, from one experiment I have n observations, from another experiment I have another data record of n observations and so on. So, for each such experiment, so let us say I conduct r experiments and in the big R, and this is the kth experiment. So, this xi superscript k is nothing but the observation from the kth experiment, and I have r such experiments. So, which means for each experimental record I can construct one x bar, and I have as a result r x bars. Now, extend this r to infinity, that means I have performed infinite number of experiments. Why have I performed infinite number of experiments? Maybe to see all possible outcomes perhaps, and if I take the average of all such x bars, that is my mu, and which we call as the expectation of x bar, right. So, that is the interpretation of mu x bar. Of course, we will talk more about this later on. So, the variance is defined as the average of the distance, squared distance of the mean from the outcome or the outcomes from the mean, whichever way you look at it. So, we say that the sigma square measures how far the outcomes are spread around the center. So, it is actually a central moment, it is not a pure moment. A pure moment would have been pure second order moment would have been integral x square f of x dx. This is a central second order moment, meaning that we are measuring, we are calculating this moment around the center. Now, of course, these are very common moments and cumulants in statistics, and this sigma square for a random variable, if it is with respect coming out of a random phenomenon, then it is a measure of the spread of outcomes, or as we had just discussed, if this random variable corresponds to some value or number that I am calculating again out of the observations, which we call as a statistic, then it will measure, it is a measure of the error in average error in the number in x bar, for example, with respect to the truth. Now, often when you turn to estimation like we just discussed, for example, sigma square x bar would be a measure of how precise an x bar the x bar is as an estimate of mu. And this variance is very important, because lower the variance, lower is the spread of outcomes. In fact, the limiting case is when sigma square x goes to 0, then what happens to the randomness in x? Well, the random x ceases to be a random variable and becomes deterministic. Again here this variance should not be confused ever with the variability that you see in time for any signal or any data. That is variability computed across time. Here the variability is being computed across the ensemble, across the sample space or the population. All right. And in defining the variance, we have used the previous expression that I gave you, expectation of g of x is integral g of x f of x dx. All right. And a positive square root of this standard variance is known as a standard deviation. And you can also rewrite the variance as expectation of x square minus mu square, clearly telling you that if there is a random variable which has 0 mean, the second order moment, which is expectation of x square and variance coincide. And as I said earlier, large variance indicates that the outcomes are spread widely far away from its center. Now, as usual, what is the variance of it? We talk about the discrete random variable case. Again, we replace the integrals with summations, otherwise nothing changes. You have instead of probability density function, probability mass functions. And as an example, if x is a binomial random variable, again where you have n trials and you are looking at x number of successes with p being the probability of success, then you can work out the math. Expectation of x minus mu whole square is n times sigma variance of x. The reason we are simply adding them up is because the trials are independent. You should remember that. And then it works out to be np times 1 minus p when you work out the math. I am not going through the math because the purpose of this lecture is only to review. As an example of the variance for the continuous random variable case, you can look at again the Gaussian distribution, and when you work out the math, it turns out to be sigma square. And again that is this sigma square is nothing but a sigma square that we see in the PDF. So, again we now understand the reason for which we have used this Greek symbol sigma square early on in the PDF. Now, in the case of a Laplace distribution that we have seen earlier, the variance works out to be 2b square. So, it may be a good idea to go through these examples more in detail for your own insights and for your own learning. These are just examples to make you comfortable with expectations. In general, we are more interested in the statistics and hypothesis testing part in this course. In a full probability and statistics course, we would have more time to go through the detailed derivation of the answer. Now, very often we may work with scaled random variables, that is, I may have a variable x and I may construct a new variable y which is alpha x plus beta. You will see this often in linear regression, for example, where I have two random variables x and y, and I think of y being linearly related to x. It is not exactly linear, this is called an affine relation. Linear would be simply y equals alpha x. So, when I have when I know the mean of x and variance of x, can I, and of course knowing alpha and beta, can I know the mean of y and variance of y? Of course I can. So, simply apply the expectation operator, and remember that the expectation operator is a linear operator. As a result, mu y is alpha mu x plus beta. All you have to do is apply the expectation operator. Expectation of y is alpha times expectation of x plus beta. That gets you the answer in 12, equation 12, and likewise the variance of y can be obtained as alpha square times sigma square x. Now, what you should observe is that the variance in y is not dependent on beta at all, because what beta is doing is simply causing a mean shift in x. You can say, so you are shifting the mean, of course scaled by alpha, as you can see from equation 12, but variances are anyway measures around the center. Therefore, changing the center should not cause a change in the variance. So, that is how you should interpret the result. And finally, there are many situations where we may add up variables that are Gaussian distributed in a linear way. As you can see here, suppose I have y, in fact the notation here should have been uppercase, just note that. So, if I have n random variables a big x1, big x2 and up to big xn, and I am constructing a new random variable which is a linear combination, assume now that these n random variables x's are falling out of a Gaussian distribution and are so called uncorrelated. We will talk about the correlation shortly. Then y is also a Gaussian or normally distributed variable, with the mean being, again you just have to extend the results that we have seen in the previous slide where we talked about scaled random variables. So, if you simply extend those results, you get mu y as being a linear combination of the means of the respective random variables in the same proportion as y, and sigma square y being sum of a1 square sigma 1 square and a2 square sigma 2 square and so on up to a n square sigma square n. This is quite useful for us later on when we are trying to derive the distribution of x bar, for example. We saw x bar as being an average of n observations. Suppose those n observations are falling out of a Gaussian distribution, then I can, using this expression, I can calculate the PDF of x bar, or of course, because once I know the mean and x bar, first I know if each x is falling out of a Gaussian distribution, x bar has a Gaussian distribution, and secondly the mean can be calculated knowing the means of the respective observations, and variance can also be computed. In effect, I know that x bar then has a Gaussian PDF with the mean given by mu y as I have shown on the slide, and variance given by sigma square y again as shown in this slide. So, you see straight away we are able to use this result to compute what is known as the sampling distribution. This term is something that we will talk about more in detail in the next lecture. And that also takes us to the very familiar central limit theorem, which essentially says if I have n random variables, but the relaxation here is this n random variables need not come from a Gaussian distribution. Earlier we had seen specifically for a Gaussian distribution. Now we are saying what if the observations or these random variables are falling out of a non-Gaussian distribution, but all of them falling out of, let us say, identical distribution, same distribution, and that they are independent. So, there are two relaxations here. One, we have moved from a Gaussian to some general distribution, but they are identical, and two, we have moved from uncorrelated to independent. Both of these terms will become clear shortly. When I take such random variables and add them up to produce a new random variable y subscript n, then as n goes to infinity, that is the number of such random variables I am adding up goes to infinity, the distribution of y minus n by sigma root n follows a standard Gaussian distribution. That is very easy. First thing for you to show is the expectation of y, that is average of y is nothing but n times the average of x, because all x's are falling out of an identical distribution. And again you show that the variance of y is nothing but n times sigma square x. Therefore, the standard deviation of y is simply root n times sigma, and we know that any, and then of course, the only thing that is not obvious which the theorem is telling us is that y, when n becomes very large, this new variable y follows a Gaussian distribution, that is all, and that is what we have used in writing this theorem. Of course, the proof of this is available in any standard text in the literature everywhere. This is a result that we will use later on to derive what are known as sampling distributions or distributions of x bar and other statistics. So, with that we come to a close on the review of the probability and the moments of a PDF. There are other moments of a PDF that one can think of, such as skewness, which is a third order central moment, or kurtosis. Skewness is a measure of symmetry, for example, and for a Gaussian distribution skewness is 0 because it is a symmetric distribution, and kurtosis is a measure of another feature of PDF and so on. But we do not worry ourselves with higher order moments, because it is sufficient to know, and in this 10-hour course that is all we can discuss. Now, we move on to the bivariate analysis, as I had mentioned early on in the lecture. Very often we may be dealing with more than one random variable as in linear regression. For example, in thermodynamics we know that temperature and pressure of an ideal gas are related at a fixed volume. So, I have temperature measurements, I have pressure measurements, both have randomness in them, and I want to analyze them jointly. I want to see if temperature is linearly has a linear relation with pressure as predicted by the ideal gas law, for example. Then what would I do? I have to now analyze this temperature and pressure jointly, or it is believed that height and weight of an individual in biomedical field and in the medical field, you know that the height and weight of an individual are believed to be related to each other. So, I have an individual for which I have taken the height and weight and looking at an entire population, I would like to know how they are related. Again, I have to analyze them jointly. When can I analyze these individually? When there is no relation between them, but we are not interested in such situations anyway. So, for this purpose we introduce typically work with what is known as a joint PDF, because now it is like two students working on a project together, that they have probably linearly influenced each other's thoughts. Then we have to evaluate them jointly, it becomes difficult to evaluate them independently. So, same case here. Now, we are dealing with continuous valued random variables, all the notions of density, distribution and so on carry forward, except that in place of univariate we have joint functions, that is all. So, the density, joint density now once again helps me in computing the probability that these two variables, again it should have been x and y, big X and big Y, taking on values between x1, x2 and y1, y2 respectively. So, now we are looking at a cell, we are looking at a two dimensional plane, we have moved from a single dimensional real axis to a two dimensional real axis, assuming they are all real valued. Now, we can ask many questions in this situation, among which two are of interest to us. First of all, we can ask what is the probability that x can take on values between x1 and x2 regardless of the outcome of I do not care what is the weight of the individual, I randomly pick an individual, what is the probability that the height of the individual is between 5 and 6 feet, for example. I can ask that, it is a very valid question to ask, and vice versa. Here is where we come across the notion of marginal density. On the other hand, I can also ask what is the probability that given that the weight of an individual is 50 kgs, that the height is between 5 and 6 feet. Now, obviously, that is going to be different from the earlier one where we are looking at unconditional probability. So, in the first case we are talking of unconditional probability, now we are talking of what is known as a conditional probability. If you recall, we had talked about this in the previous lecture as well. When would these two be identical, the unconditional and conditional probability? Intuitively, when x and y are independent of each other. When height and weight, for example, have no influence on each other, then the conditional and unconditional would coincide. Of course, there are strict theoretical considerations when you talk of saying given that the weight of an individual is exactly 50 kgs. But strictly speaking, we are not supposed to be talking that way, because as we said in the previous lecture, for continuous valued random variables we do not talk of probabilities that a random variable takes on an exact value. The way this conditional probability should be interpreted therefore is, what is the probability that the height of an individual is between 5 and 6 feet, given that the weight of an individual is in a very small vicinity of 50 kgs. So, but we do not keep saying that, but you have to remember that in your minds. So, with that we introduce the notion of marginal density and independence, right. We have just spoken of that. Marginal density is like on your page, it is the page of a book is two dimensional, we have margins. So, remember when we walk along one dimension and adding up all that we encounter across another dimension, we end up with marginal density. So, the marginal densities are typically denoted, for example, the marginal density of x is denoted by f of x subscript x. That subscript x is telling you that it is a marginal density, it is not necessarily the density of x alone. There is a difference between marginal density and just PDF of x. The difference is that the marginal density is obtained by adding up or integrating the density along the y axis alone, whereas the density of x is taking into account probably all other factors also that are related to x. So, there is a subtle difference and therefore, it is important to maintain that notation f of x subscript x. Likewise, you can define marginal density of y as well. Now, we say that two random variables are independent if the joint PDF can be written as a product of the marginal densities, respective marginal density. This has a strong relationship or resemblance to what we wrote in terms of probabilities. We say two events are independent if probability of A and B occurring together is probability of A times probability of B. Once again, do not confuse your independence with mutually exclusive events, that is different. Mutually exclusive events, probability is 0 that both will occur together. And as we spoke of conditional density earlier, where we said given the weight of an individual is 50 kgs, what is the probability that the height is between 5 and 6 feet. Such probabilities can be calculated by the use of what are known as conditional densities. And this conditional density expression is arrived by using Bayes theorem or Bayes result, which says that it is the joint PDF divided by the marginal density, again there should have been a subscript there, marginal density of x. Likewise, you can, this is the conditional density of y given x, all right. Likewise, you can write f of x given y, which is f of x comma y by f of y. And now, we can go back and relate this to independence, that is, suppose two events are independent or sorry two variables are independent, then we just said earlier that the conditional probability and the unconditional probability would be identical. Likewise, the conditional density and unconditional densities would also be identical. I am just stating this without any proofs and so on. So, f of y given x would be the same as f of y, or f of x given y would be the same as f of x. Now, using this definition and this the other relation that we just said, it is straightforward to show that f of x comma y would be simply f of x times f of y. Right. So, just combine both and you will get that. So, that is the other definition of, that is the definition of independence that we saw in equation 15. Okay. Now, for the final part of this lecture, we talk about covariance or correlation, which is the most ubiquitous measure that is used in data analysis. So, if you are going to continue in data analysis, then you should be really clear about the notion of correlation, what it does, what was it originally devised for, and how is it defined, right. The basis for the definition of correlation is covariance. So, we have talked about independence earlier. Independence rules out any form of relation between x and y, and we measure theoretically, at least we say that we measure that by looking at the joint density and the difference of that from the product of the marginal densities. If the difference is 0, then they are independent. If the difference is not 0, then there is some dependence. So, the question is what form of dependence exists between, for example, height and weight of an individual, or in the examples that we discussed, the highway mileage and the engine capacity. So, and so many other examples and so on. In this course and in general, we are interested, at least to begin with, is linear dependence. Is there a linear relation between two random variables? The advantage is, if there is a linear relation, then I can build linear models, and the math associated with the estimation of linear models is so easy compared to the math associated with the estimation of nonlinear models. So, the entire modeling or the regression literature is very rich for linear models therefore. Now, covariance is a measure of the linear dependence between two random variables x and y. We may not prove that, but we will discuss that a bit in detail. First, the definition of covariance. It is now the second order central moment of the joint PDF. Earlier we talked of variance, and in fact, you can see from the definition in 17 for the covariance, if I set y equals x, then it simplifies to the definition of variance. And you can see it is a double integral, again minus infinity and plus infinity are only symbolic, they are the respective extreme values for x and y. And mu x and mu y are the means obtained from marginal densities of x and y respectively. Alternatively, you could write, if you do not like those double integrals in equation 17, you could write sigma xy as expectation of xy minus expectation of x times expectation of y. Now, this is a very nice resemblance between this and the expression that I spoke earlier in terms of PDFs. Let me point that out. While introducing covariance, that independence theoretically can be thought of as a difference between f of x comma y minus f of x times f of y. If this is 0, so let us say that there is some gamma measure which does this. Okay, let us just as a purpose of discussion, this is not really used in practice. On the other hand, looks at the difference between expectation of the product and the product of expectations. And we say that two variables have a 0 covariance when sigma x y is 0, that is when expectation of x times y is the same as the product of expectations. Look at the relation resemblance of this, they are not identical, because here you are looking at a product, this is just a joint PDF, but I am just trying to point out the similarities between these two expressions. This is, if this is the case, then x and y are not linearly related. If this is the case, then x and y are not related at all. Obviously, this is a much stronger condition compared to this, but in practice, since we are worried about linear dependencies, we work with this. So, this is of course theory. In practice, we will have to use estimators for covariance and see if that estimate is very small and subject to hypothesis test. That is exactly what we are going to do in hypothesis testing. I am going to estimate sigma and I get sigma hat. In fact, and then conduct the hypothesis test whether whether the true sigma is 0 against the alternative sigma is not equal to 0. Now, there is a problem with this kind of a hypothesis test primarily because if you look at the definition of sigma, it depends on the units of x and y, that is the main problem, right. And second problem is I do not know what is high sigma, low sigma and so on, but we will not worry about so much as its dependence on the units, and it is with that purpose that normally one works with correlation, which is a normalized covariance. So, rho x y is a normalized covariance which addresses two issues in one shot. One, that now this has become unit independent of x and y. So, if you look at temperature and pressure, whatever units you use for temperature and pressure, the correlation comes out to be the same value, whereas sigma would work out to be a different value depending on the units. Moreover, you can show that correlation is bounded above by unity in magnitude. So, the maximum possible value for correlation, magnitude of correlation is unity, and then with this correlation I know when sigma is 0, rho is 0. So, conducting a hypothesis test on sigma 0 can be replaced with rho being 0 and alternate hypothesis being rho not equal to 0. That is exactly the kind of hypothesis test that we are going to study later on, all right. And we will talk about a bit more about this correlation. What does equality, what does it mean when correlation becomes equal to 1? We just spoke of this correlation as a normalized measure, and correlation enjoys all the properties that the covariance satisfies. In other words, if the covariance is a measure of linear dependence, correlation is also a measure of linear dependence, and this inequality that correlation is bounded above in magnitude by unity can be proved by Chebyshev's inequality. Again, the proof is available quite widely, and in particular we are interested in asking what does correlation hitting a value of 1 mean. Correlation, when it takes a value of 0, we know x and y are not linearly dependent, which means some nonlinear dependence may exist. So, then one has to conduct tests of nonlinear independence, we will not worry about that. the fact is when correlation hits a value of unity in magnitude, then this is only possible when y and x are linearly related. That is, this is both a necessary and sufficient condition. I am only showing one part of it here for your convenience. That is, if y is related linearly or affine way alpha x plus beta to x, then correlation is 1. Of course, without loss of generality, for simplicity's sake we will assume beta to be 0. So, assume y is alpha x and then you work out the expectation. We have already seen if y is alpha x, mu y is alpha mu x, sigma square y is alpha square sigma square y. This is something that we have seen earlier. So, we are just using a known result and plugging in for rho. The expectation of x comma y is alpha times expectation of x to the whole square minus sorry, it should be expectation of x square minus expectation of x whole square divided by the product of sigma x times alpha times root x, but positive alpha, because we know that sigma y is the positive square root of the variance of y. So, when you work out all of that, you get rho to be plus or minus 1 depending on the sign of alpha. So, the magnitude works out to be 1. Of course, I have only shown that if y is alpha x or alpha x plus beta, then rho is 1, but you can show the other way around also. Rho equals 1 implies that y is alpha x plus beta. So, this is a fundamental result in data analysis, because it tells you that when correlation hits a value of 1 or estimates are very high, very close to 1, then a linear model will do a very good job of predicting y given x. That means, you can live with a linear model as far as prediction of y is concerned using x. If correlation values are low, then what does it mean? Well, what it means is that there is a deviation from the linearity assumption, and that deviation could be presence of noise, presence of non-linearity and so on. We do not discuss that at this moment. This is just to introduce and review concepts of correlation. And we have just said that two variables are uncorrelated if, just to reiterate, if the correlation is 0 or expectation of x y is the same as the product of expectations. But this is a weaker requirement compared to independence. What this means is independence implies uncorrelatedness, but uncorrelatedness does not necessarily imply independence. Now, the result is that if x and y follow a Gaussian distribution, that is a bivariate Gaussian distribution. The bivariate Gaussian distribution has a different expression from what we generally think of as an individual Gaussian. There is similarity, but they are a bit different, and I will just write that for you. So, the bivariate Gaussian distribution, if two random variables x and y have a joint Gaussian distribution, their phi times determinant of sigma, I will tell you what is a sigma, square root of the determinant of sigma times exponential let us say this there is a vector x. I am going to tell you what is that vector x, and this is a vector mean transpose sigma inverse times x minus mu x, and there is a half here. So, what is this sigma and what is this x? First, let me write what x is for you. X is nothing but the vector of random variables x and y, or you may think of this as z if you do not like x. So, z is this vector of random variables x and y, and sigma is the variance covariance matrix that normally one sees in the vector random variable case. So, it has the variance of the individual random variables along the diagonal and the covariance on the off diagonal of the matrix. So, now this is a symmetric positive definite matrix. It is symmetric because sigma x y is the same as sigma y x. Covariance is insensitive to the ordering of the subscripts. That means it does not know whether x causes y or y causes x. It simply looks at the dependence between x and y. Therefore, it is a symmetric matrix and further it is positive definite. So, you can guarantee therefore, sigma inverse exists. That means its determinant is not 0 unless sigma square x or sigma square y is 0 and so on, but we will rule out such pathological cases. Then if f of x comma y is this, then x and y are set, this of course is a determinant here. Then we say x and y have a joint Gaussian distribution. Now, a subtle point is if x and y are individually Gaussian distributed, it does not necessarily mean that joint distribution is also Gaussian. Examples can be given, but this is just a point for your remembrance. So, now when that is the case, when x and y have a joint Gaussian distribution and they are independent and they are uncorrelated, then you can show that they are also independent. That is, if what happens when x and y are uncorrelated, the variance covariance matrix, that big sigma that we have written on the board, is a diagonal matrix. That means sigma x y is 0, in which case it becomes a diagonal matrix, right. Now, you can show that if that is the case, you can factorize f of x comma y as f of x times f of y, and that means x and y are also independent, but this is only true for the bivariate Gaussian distributed case. In fact, you can extend this to the multivariate Gaussian distributed also. So, any set of random variables that have a joint Gaussian distribution and are uncorrelated, that means there is no linear relationship between them, then it also means there is no nonlinear relation, absolutely no relation between them at all. And that is the speciality that you can say about a Gaussian distribution. It does not apply to any other distribution necessarily. So, with that we come to the closure of the review of probability and statistics. To summarize, what we have looked at is in concepts of probability, we have looked at axioms of probability, then we learned what is the notion of a random variable, probability distribution function, density functions, mass functions, and then we said it is hard to work with PDFs in practice. Therefore, we will work with the moments of the PDF, mean and variance, which is what we have seen also in the examples. We said average, variability, this is what we spoke of. In none of the examples in hypothesis testing that we looked at, we tested the PDF. We talked about the PDF, if you recall, and that is the case also in reality. And then we went on to learn what are the interpretations of mean and variance in different contexts, and finally we looked at the bivariate case, where we learned that for the bivariate case or even the multivariate case, one has to work with a joint PDF. Again, the same story in the univariate case, we said the PDFs are hard to work with, therefore, we went to the moments case. So, in the bivariate case, from the joint PDF we straight away went to the second order moment, which is covariance, and learned that the covariance or correlation, which is a normalized measure, is a measure of linear dependence. It is a very good measure of linear dependence, because when it hits a value of unity, that is a correlation, when it hits a value of unity, then there is a perfect linear relationship between those two variables. Any deviation from that would mean that there is something else in y which x cannot linearly explain. That something else in y could be noise and or some nonlinear functions of x. And finally, we also talked about independence, which is a measure of lack of any relation, ruling out all forms of dependence between y and x, but we will not worry about that anymore in this course as far as testing is concerned. However, the notion of independence is very important, because in the next lecture when we talk of what is known as a random sample, and there we would talk of the joint PDF of the observations that we have obtained, and a random sample would mean that the outcome in the first observation will not affect the outcome of any other observation. So, those n observations that we collect in the random sample are going to be independent, and with that idea we have reviewed the notion of independence early on. So, that is it. There is an R tutorial that we will also put up, go through the R tutorial, and then as far as the lectures are concerned, we will get back again with the concepts of what are known as statistics and sampling distributions, where we will talk of sample mean, sample variance, sample proportion and so on. and sample correlation. All right then. So, hope to see you again soon in the next lecture.